Hello everybody, welcome to Blue Marble Science. Today we want to talk about gravitational acceleration. Have we got proof of the acceleration of gravity? Oh, you betcha. You know, flat earth proponents absolutely insist there's no such thing as gravity. Now I know that sounds pretty silly, but that's what their leaders are telling them. And to tell you the truth, Gladys and I have had about enough of that nonsense. Now we can do a really simple experiment that will stop this debate dead in its tracks. So Gladys, are you ready? Hey, let's light that fire and have a little fun. Well, we all know gravity is real and we know it exists, but we can prove the acceleration of gravity is a real thing, and we can do that by allowing it to add or subtract from another acceleration, namely the centripetal acceleration. Here's how that works. Imagine you've got a weight on a string and you're swinging that weight around in a circle at a uniform velocity, and you're holding your hand up above your head so that the weight is traveling in a circle that's parallel to the surface of the earth. In other words, perpendicular to the acceleration of gravity. At any point around the circle, the weight has a constant velocity and a vector like the vectors you see in the diagram. And you should note that at any point, if you let go of the string, that weight would continue in a straight line, just like those velocity vectors show. But it doesn't because you've got the string attached to it, and you are pulling those velocity vectors around in a circle. That is the centripetal force that you are feeling. Now, gravity will have no effect on it as long as your plane of rotation is perpendicular to the acceleration of gravity, like we just described. But now let's consider a different situation. Let's say that we hold our hand out in front of us or to the side, and now we rotate the weight in a vertical direction. Now we are in the same direction as the acceleration of gravity. So for instance, as you are rotating the weight around from point A over the top, point B, and around to point C, gravity will actually add to the centripetal acceleration. But as you reach point C and start down around the bottom half of the circle, gravitational acceleration will subtract from the centripetal acceleration. And this can be measured. And that's what we're going to do. I think this will be a lot more clear after you watch the following video. Well, if any of you watched before, when I was demonstrating centripetal force for gyranism, I used the same little rig, which I've now modified a bit. Before, I just spun the thing by hand to show that centripetal force is going to always be toward the center of a rotating system like that. Okay. This time, we're going to do it differently. We're going to demonstrate the acceleration of gravity using this little rig. Gravity, of course, is that direction. At least it is in my neighborhood. So you can see the accelerometer. Let me get these scales about the way we want them. So the green line is acceleration in the y-axis, that way positive. The x-axis is the red line, acceleration positive in that direction. So we're going to mount this on this rotating platform, and we're going to measure the acceleration of the centripetal force that way, and you'll also see some acceleration due to the starting and stopping of the rotation of the platform. Now we're just doing this with a drill motor, and it doesn't maintain a perfectly constant speed, so there'll be a little bit of variation, but that's okay. It shows what we want to see. So there we go. Let me see if I can spin this for us. You can hear the speed varying slightly, but that won't hurt us now. All right, let me pause that. Now the green is the centripetal force, the acceleration positive toward the center. The red, this little blip at the front here, this is where we started. That's that's when we accelerated initially, and then that all just levels out, as except for the minor variations in speed, which are small changes in acceleration, and then that last spike is when it ended. Okay, now let's change the frame of reference for this thing. When I turn this around sideways, if I can do this, when I turn this around sideways, like that, now we're going to have the acceleration of gravity acting that direction. So adding to the centripetal force when it goes this way, when it's up here at the top, when the accelerometer is here at the top, and subtracting from it when it's down here at the bottom. But it will also affect, you'll also see the change in acceleration of the rotation. So let me put the accelerometer back in. Same scale. Let's see if we can do this without hitting myself. There we go, get the speed relatively constant. You can still hear it speeding up and slowing down slightly, but we're going to see what we want to see. Okay, let me pause that. Now what happened? Now you can see the centripetal force is no longer a fairly straight line. You're seeing all this sine wave looking stuff as the acceleration of gravity adds to and subtracts from the centripetal force. You're seeing also the effect of gravity, the acceleration of gravity, just on the rotation. Now the red line is no longer a nice straight line. It's a sine wave too. I believe that is a pretty adequate demonstration of the effect, the gravitational acceleration, and I don't think there's any way you can question it. That's it, folks. What you just saw was a very clear demonstration of the acceleration of gravity. When the rotation of the platform was normal to the acceleration of gravity, we measured centripetal acceleration and angular acceleration just as you would expect. The angular acceleration was 0 except for the starting and stopping of the platform. Centripetal acceleration was constant as long as the platform was rotating, with just minor variations because the drill motor doesn't maintain an exact constant speed. But on the other hand, when we turned the reference frame around so that rotation was in the same plane as the acceleration of gravity, the effect was dramatic. Both the centripetal and angular accelerations were added to the acceleration of gravity, and you could see that very, very clearly on the accelerometer. Now that's an accelerometer. It doesn't know a damn thing about density. It's a cell phone. It sure doesn't know anything about density. So hopefully this has answered anyone's questions and at least helped put to rest the notion that gravity doesn't exist. Hey, thanks for watching. I hope you guys enjoyed this. If you liked it, don't forget to like and subscribe. And we'll see you on the next one. Gladys, we're out of here.